So let's go ahead and get started and think about the effect that self-weight or an evenly distributed force has on the internal force diagram. And to do that, let's of course first draw a cutout section of a beam. So let's say this is my rigid body here, which therefore deserves a dashed line, and it is loaded with an evenly distributed force. So that would look something like this. And this beam is some element cut out somewhere out of a beam. So I cut this out here and I cut this out here. And of course, in reality, I release internal forces if I do that. And the internal forces that we would release would look something like this. You remember this from your study card. I have the shear forces on both sides because I cut on both sides. And I also would have normal forces on both sides, which I am not trying to calculate right now, but I want to think about how they conceptually would look like. And to conceptualize that, I want to introduce a length here of that member that could be really anything. It could be as short as dx, it could be 5 meters or 5 feet or whatever, but I just make this x and maybe meter long. So the length right now is just symbolized by x. And now I want to go ahead and draw the diagrams below this beam that I can conceptually understand how the distributed force impacts the shear force diagram that I will draw right here. And then later on, I will draw the moment diagram right below it. And what we have to understand here to extrapolate our understanding from these pictures later on is that, of course, this is cut away as well. And so these beams are just x long as well. And what that means is that I do not know exactly what value I will have at this location, right? So I will just think about what impact this force will have. And keep in mind, we call this force usually W, and usually that's given in force per distance. And so we need to think about what that means. And remember something that we discovered last class, that we actually have a relationship between the different cases. And one of the first ones that we talked about was, well, the first one we talked about was actually that the shear force is really equal to the derivative of the moment. But another one that we also introduced is that the force case or the load case, let's call that minus W, is equal to dV dx. And we can now think about what that means in the context of the evenly distributed force here and how that impacts the internal force diagram. So we have a force that's actually pointing downwards. So because it's pointing downwards, that's where the negative here is coming from. And we are now going down with a certain force per a certain distance. So for example, let's pretend that W would be equal to 10 kilonewton per meter. And if I would have that unit, what would that mean? That would mean that my force pushes down with an additional 10 kilonewton for every meter I move from left to right in this case. So if x was 1 meter, I would have a total of 10 kilonewton on the system. If x was 2 meters, I have 20 kilonewton because I multiply it by 2, and so on and so forth. And so you can already see from here and actually from here, because this is a constant, that here for the shear force diagram, I must have a slope, right? So what I really would end up with would be a sloped line or a linear function that in this case would slope from the top left to the bottom right. And I purposely am not drawing it symmetrically in this case because remember that this location here could just be x1 and this could be x2, and therefore we could have any value as long as it slopes down in this direction, because we have actually an addition of, for example, 10 kilonewton per meter downwards as my x increases. And remember that this applies, or what we did last time is that every time we had a concentrated force, the internal force diagram for the shear force really jumped down. And so that is an important concept you need to understand, that the jump is actually reflected here as well, except the jump is continuous really, right? So for every meter that we're moving from left to right, or for every increment I should really say, we're actually jumping down. Except we're not going to the right and then jump down, go to the right and then jump down, go to the right and then jump down. We're going down all the time with W as we move from left to right. But you want to think about this as, for example, that every meter you go to the right, you jump by whatever value. So in our example here, 10 kilonewton. So if I were to draw this conceptually speaking, then I would have a jump here, or a step that would jump down by 10 for every 1 meter. And I could do that again for the adjacent portion here, and so on and so forth. So it would always be the same. But of course we're trying to do this conceptually here right now, so I'm not hung up on the values. I don't want to worry about the values. I want to worry about the fact that here I have a constant function which is pushing down, and therefore, because my reference fiber is on the bottom, I have a slope that slopes from top left to bottom right. And this is true for the shear force at all times if you have a distributed force. Of course, your starting value and your end value may change a little bit, but it is always true. And therefore, we actually always end up with a linear function. So let me make space here and clarify that we have a linear function. And of course, this function will describe the shear force. So we will call this the shear force of x. And to describe that, let me say that I have a value right here as a starting point, which of course is arbitrary in this case. But remember that I started at x1, so I call this value v of x1 really, right? So this is the shear force value at x1. And what I end up with then for my linear function, because I'm starting here and I'm going down, 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 down with a linear fashion, I will end up with v of x1 as the starting value, in this case, minus w times x. And let's talk about this real quick. The v is, of course, in, let's say, kilonewton, or in force units really. And then I have the w, which is in kilonewton per meter, for example. And my x is really in meters. And so therefore that works out, right? So the w is really the function that describes, in this case, the constant function of the distributed force. So that's where I come to this equation here, which works out to be kilonewton. And that's important, of course, for us to end up with kilonewton values everywhere along this line, because our goal is to describe what is the value here, what is the value here, what is the value here, and so on. So everywhere along x. And those x values everywhere along this line will actually help us to understand how to interpret the moment function, which of course will become a function too now, because we see this relationship here. So what we want to do is we want to end up with the moment diagram here on the bottom, that of course is going hand in hand with this and this function here. And since we already see this relationship here, we can of course also, at least conceptually, integrate. You can do it mathematically too, but sometimes there are some traps you will fall into. I talked about that in the last lecture, but remember that you can integrate from the shear force to the moment diagram. And what does that really mean? The integration is really reflected as the inverse of what you see here in a sense. And so I want to talk about the meaning of this function here, or the derivative. So what is the derivative really? The derivative is the slope, right? And I know that you learned that in mathematics before, but I have learned in the classroom that students sometimes have a hard time to really interpret this when it comes to physical meaning. For example, the relationship between the shear force and the moment diagram. So I want to be very explicit about that. So let me repeat that. This graph is the derivative of the moment. And what does that mean? That means that every value along this graph really describes the slope of the moment function. And so we can use that to our advantage and really apply our understanding of the shear force function. For example, I can say that I have a very large value here, at least compared to all other values along that graph. In fact, it's probably larger than this value here, so I call that a small positive value. And then here I have a small negative value, and here I have a large negative value, or the smallest value of all of them here. And of course, the one thing I never need to explain to my students is that here I have a zero value. So here v of x is really equal to 0, or the shear force at that location is equal to 0. And therefore, everybody understands that when you go to the primitive, or the parent function as I call it sometimes, I have a local maximum or minimum here. And that is something we can often agree on in the classroom. What we don't agree on is really what function comes from the integration from here to here. Of course, you would think right now, this is a linear function. Therefore, of course, I have to go up by 1x, and therefore this will become a quadratic function. And that is definitely true. And of course, that is also something I can get across easily. What I don't get across easily is in which direction the quadratic function will be pointing, if you want to call it that way. So for example, it could be belly up, as my students call it in the classroom. It could be belly down. It could also be like this. But in reality, it cannot be anything else than a very specific function that I want to develop with you right now. And that relates to these values that I drew here. So remember that this is the derivative of the moment, and therefore this value here describes the slope at this location. So let me actually call this here, for example, xa, and then here I call this xb, and then xc and xd. And what you need to understand is that this value here describes the slope of the moment function at xa. This value describes the slope of the moment function at xb, and so on and so forth. So this is a smaller value, and this is an even smaller value. And of course, somehow we all understand that for the 0. So I can actually go ahead and draw the moment function, and I can draw the tangent. So let's pretend here I have a tangent that is 0. But now let's look at xa and xb. At xa, I have a very steep slope, right? It's a larger value. So let's just pretend that's somewhere there, the tangent. And then at xb, I have a smaller slope, and that would look like this. And at xc, I have a negative slope, right? That's important to understand. And that negative slope is somewhere here. And then at xd, I have a larger negative slope, or a smaller slope, if you want to call it that way. And so that would look like this. And so let's pretend that my tangent is right here, and here, and here, and here, and last but not least here. And now I can connect those points and really draw my parabolic function that could not take on any other shape than this. And first of all, we understand that it's positive, and that is now our complete moment function. And of course, we understand that we cut it somewhere randomly, so we actually also end up with a value of m of x1 here, and then here m of x2. But again, I'm not worrying about those values. What I worry about is that here I have m max, and that I actually related this point to this slope and this point to this slope. And please note that this is positive here. And positive means that this is a positive slope. Remember what a positive slope is, from bottom left to top right in a 2D coordinate system in the first quadrant. Whereas a negative slope in the first quadrant would be from top left to bottom right. And so we related each of these shear force values to the slope of the moment function, because we know this here. And therefore, we can unmistakably draw the parabolic function and the shape of this moment diagram. And let's talk about the unmistakably part here for a second. So students sometimes tend to think, this is positive here, therefore my moment diagram must be positive. But you can already tell from this diagram that this is not the right logic, because here it's negative and my moment diagram is not negative here. So what does the positive and the negative mean? The positive and the negative relates to the slope only. And slope, again, has something to do with in which direction the diagonal line is sloping, right? So either up from left to right or down from left to right. And you can see that everywhere here where the shear force is negative, the slope is going from left to right downwards. Whereas here where the shear force is positive, the slope anywhere along this function is moving from left bottom to top right until we hit 0 here. And that's where we then turn around. And that's exactly shown here. So mathematically, students always know this, but really turning this into a shear force to moment relation is sometimes challenging. However, I hope this will help you to clarify this and to understand that this will always work, because we start with a constant function. In fact, let's understand here that this is always a constant. And then, therefore, we end up with first a linear shear function, but then we have a parabolic function for the moment. And that is always true as long as you have a constant or evenly distributed force. So under self-weight, which is really represented by this, under self-weight you will always end up with a linear shear force function and a parabolic moment function. And don't get me wrong, of course you can have distributed forces that actually push in the other direction. Then this whole thing would flip around. So for example, here we would have negative values and here we would have positive values. And then also the beam would not be smiling, right? Remember, this beam is actually smiling, therefore everything has to be positive. But if you push up with a distributed force, then the beam would be frowning and therefore everything would have to be negative. But you will learn this through application. In fact, we will actually apply this today. We will not calculate the values everywhere along the line, and we will not set up functions, really. That is our goal in our next lecture. But to really understand how these diagrams come about, we really needed to talk about the relation here between the distributed force and the shear force, and the shear force and the moment, all for effectively self-weight or evenly distributed forces. So the next thing for us to do now is to analyze what happens if we make this a little bit more complicated, and what happens if we don't have self-weight or evenly distributed forces anymore. What happens if we have non-evenly distributed forces?